Alrighty, so let's get started. Today, this video, we're going to be doing electric fields. Last time we talked about the Coulomb force due to on a charge due to another charge, and we found it was 1 over 4 pi epsilon naught Q1 Q2 over r squared, where what we have is two charges, Q1, Q2, separated by a distance r, and we want to know what's the force between them. Attractive, repulsive, of course, that's what we found. And then we also saw that because this is a vector quantity, then if you have multiple charges, not just two but three, then we have something like this. Then you have a force due to this guy and a force due to this guy acting on this charge, and we would add up these forces vector-wise, and so let's call this Q1, Q2, and Q3. Then the force on 3 is going to be the force on 3 due to 1 plus the force on 3 due to 2. And of course, given that these are in different directions, we do x and y components, but each one of these is our 1 over 4 pi epsilon naught Q1, Q3 over R13 squared plus 1 over 4 pi epsilon naught Q2, Q3 over R23 squared. Notice for both of this particular thing, even if there were 50 charges, all we would do is just keep adding these things together, and each one always has this form. The force is this 1 over 4 pi epsilon naught times the Q that that's applying the force to us over the distance to that guy. So I'll call this the force on on x. And let me redo this. The force on particle x due to 1 is 1 over 4 pi epsilon naught, the charge Q1, divided by the distance from 1 to x squared, multiplied by our Qx, right? So if we have, here's some charge here, call this Q1, and we're going to place a charge here, Qx, and I want to know what force is he going to feel. And then if I put another charge, maybe there's a Q2 and a Q3. Okay? Each one of these Q's is going to give a force to Qx, and we add all these forces together. But each one is always of this form. It's the charge that's going to feel the force times this mess over here, which is a constant, 1 over 4 pi epsilon naught. The charge that's giving us the force divided by the distance from that charge to us, right? Well, if every single one of these is always of this form, it's just that one is Q1 over R1, Q2 over R2, Q3 over R3, blah, 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 but each one is always multiplying a Qx, then what I could say is the force on a charge x is equal to something, I'll call it E, multiplied by our Qx, right? Where the something is this bit of nonsense there. Okay, it's just a way to make the equation look a little simpler. E is 1 over 4 pi epsilon naught Q over R squared, right? That's what E is. So if I multiply E by our charge, I will find out how much force our charge will feel. So the physical intuition here is that this thing E that I've created, I've kind of simplified down into a single number E. This is basically a number that tells me, or a quantity that tells me, if I place a charge Q at this point, that charge Q will feel this force in this direction, right? So E is created by all these other guys that are just sitting there, and I go and move my Q right there, and then I say, what will this Q feel because of all those other things out in space? Just like if we've got the solar system, we have all the planets moving around the sun, and then I say, okay, if I were to put a satellite out here in this location, what will he feel by gravity? Well, he'll feel something due to the sun, something due to the earth, something due to the moon, something due to the Mars, blah, blah, blah. Well, the sun, the moon, the earth, the Mars, those are all there already. They're the source of the force I'm about to feel, which is gravity. Same thing here, but with electric charges. I've got these charges, Q1, Q2, Q3, sitting there on the table. They're just sitting there. And now I'm going to bring my little QX, and I'm going to say, if I put it here on the table, what will he feel? He's going to feel a force due to all those sources. So this E, I'm going to call it the electric field. Now, a field is something very important in physics. We get it all the time. The more fundamental you go, the more and more you see fields pop up. But all a field is take all of space and assign at every point in space a number or a vector or something, some quantity. So here's space. And I say, okay, here, 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 here. At each one of these locations, there's going to be a number. And maybe this is, let's say, 60, 61, 58, 62, 60, 59, 57, 58. You get the idea. So at each point in space, all over space, we're going to assign a quantity, and that quantity tells us something. In this case, this is called the temperature field. So in your room, you turn on the AC, and pretty much anywhere you walk basically feels the same. However, you know actually, if you go over by your window with the sun shining outside, then likely near your window it's a little bit warmer. And over by your AC vent, it's a little bit colder. And then everywhere in the middle, it's about the same temperature, but not necessarily exactly. And that's what I'm showing here. Pretty cold in your room, but, okay, pretty much 60 degrees everywhere, but it's slight changes. That's a field. There is a temperature everywhere, so everywhere has some quantity, some number, and that number tells you the temperature there. And of course, the same is true for all sorts of things. With, let's say, if you've ever seen the weather, a lot of times the Weather Channel or the weather guy will show the wind gradient or the wind field, which basically says how fast is the wind going and in which direction does the wind blow. So maybe you'll get something like this. You'll have, arrows, something like this. That tells you at each one of these points, maybe here it's 4, 5, 6, 4, 3, 10. Then what this is telling you is at this location, the wind is blowing at 5 miles per hour in this direction. And in this location, the wind is blowing 6 miles per hour in this direction, and blah, blah, blah. And so you get this field that's describing to you at every point in space how much wind velocity there is. Okay? This is called a scalar field because it's just a number. It's 58 degrees or 60 degrees. And this is called a vector field because not only do you know the wind speed, but you know the direction the wind is blowing. Okay? Just like numbers, fields can be scalar fields or vector fields as well. The electric field is a vector field. It says if you were to put a charge here at this location, the direction of the electric field and its magnitude tell you proportionally how much force it's going to feel. In which direction will it move? Okay? So a lot of times it's useful to, instead of every time we go to calculate with how much force a charge is going to feel, why don't we calculate the electric field due to all the sources, And then that way, it doesn't matter what charge I put there. I just put this charge, I get this number. If I put that charge, I get that number. That is to say, I want to know what is going on in the space. That way, no matter what charge I choose to use, I'll know how it's going to react. Okay? So usually it's a good idea to find the electric field and then use the electric field to calculate the force. So just as an example, let's say I've got a charge here and a charge here. So I'll call this Q1 and I'll call this Q2. I'll let Q2 be 2 microcoulombs and Q1 will be 1 microcoulomb. From here to here will be 3 meters, and from here to here will be 4 meters. Okay? Here's my question. Find the force. In fact, well, let me just erase this 1 microcoulomb for now. Q1 is sitting there. I don't know what Q1 is yet. Find the force on Q1 by Q2 if Q1 is 1 microcoulomb, Q1 is minus 3 microcoulomb, Q1 is 2 microcoulomb. Okay? Well, what one should do here is, because what Q1 is going to be is going to change, and each time I change it, I get a different answer. Instead of going through the full calculation every single time for each new Q1, let's do the general calculation for the electric field, and then I just insert my Q1 after that. So what I'm going to do is find the electric field. All right, well, what's the electric field going to be? Well, the electric field, if we remember, is our 1 over 4 pi epsilon naught Q over R squared. Okay, so I'm looking here. This is the point where I'm going to put my Q1. Q2 is the charge that's going to give me my electric field. So I have 1 over 4 pi epsilon naught times 2 times 10 to the minus 6, because it's microcoulombs, over R squared. That means I need the distance from Q2 to Q1. Well, what is this distance? Well, I need this hypotenuse. If the x side is 3, the y side is 4, I happen to know by Pythagorean theorem, then the hypotenuse is 5. So this is going to be 5 squared. So plugging in my numbers, 1 over 4 pi epsilon naught, that's just 9 times 10 to the 9, times 2 times 10 to the minus 6, divided by 25, and I get an electric field of 720. Okay? So that's the electric field. Now that I know the electric field, I can say the force on 1 due to 2 is the electric field due to 2 times the charge 1. Well, the electric field is 720. Charge Q1, well, for part A, it's 1 times 10 to the minus 6. So I get 7.2 times 10 to the minus 4 newtons. Okay? So that's how much force charge 1 will feel for part A. But what about part B? And here's the nice thing. I don't have to do that first calculation again. It's still 720. But now what the charge has to be is my 3 microcoulombs. So 3 times 10 to the minus 6. Okay, so 720 times 3 EE minus 6 gives me 0.00216. And of course the same for part C. I just plug C's charge in. Also notice that what I'm doing here is just getting a value. I'm getting a magnitude of the force. This is not telling me the direction. All I know is how big of a force will I feel. If I wanted the direction, then of course I have to make sure I keep the directionality and the vector nature of this stuff. But what we're going to do in this class is when we have problems with multiple charges, a whole bunch of charges. Obviously, I don't want to have to keep track of the directionality of each single one of these guys, so I'm usually just going to be asking for the magnitude of the force. So the magnitude of the force, I just need to know the number. I don't need to know whether it's positive or negative. Is it moving to the left or the right? If, however, I tell you use the Coulomb law, so what we did last time to calculate the force, then yes, you need magnitude and direction. But when you're doing it through the electric field, if I say find the electric field and then use the electric field to find the force, I mean just find the magnitude of the force, which is what we did here. Okay? So this is just a simple, quick little introduction to electric fields. Very fast. Nothing big here. All I'm doing is taking what we did last time, the Coulomb force, and just saying I've noticed this kind of setup is always true, and it's always multiplied by the thing I'm trying to apply the force to. So if we calculate stuff about the sources, that's fundamental. And now I'm the guy sticking this Q2 sitting there, and I can change which Q2 I want to use. Using the electric field is going to be a very powerful technique. Okay, we're going to get into what's called Gauss's law, Stokes' theorem, the divergence theorem, all sorts of fancy calculus things, and they're all going to be very important using the electric fields rather than purely the forces. Okay? But again, you can get the force from the electric field because we've defined the electric field from the force equation itself. Okay? So again, what is the electric field? The electric field is just the K, the 1 over 4 pi epsilon naught business, times Q over R squared, where the Q is the sources that are applying this force. So I'm going to stick a Q somewhere. All the other charges that are already there, they've created this electric field, and the electric field tells me how my charge will move. In fact, if I were to draw a picture, so if I said, okay, this is what the electric field looks like here. Let's say that's what the electric field looks like on this space, and I gave you this force or this charge, and I placed the charge right there, and I said, in which direction will this charge move? What's good about the electric field is it tells you in which direction and the magnitude of the force a charge is going to feel if placed at that location, if the charge is positive. So if I place a positive charge at this blue point, then the electric field tells me how will this blue charge move. It's going to move in that direction. If I put a charge here, it's going to move in that direction. If I put a charge here, it's going to move in that direction. Okay? So that's what the electric field is telling me. It is a value assigned to every point in space that gives you the magnitude and direction of how a charge would feel a force, how much of a force the charge will feel due to all the other charges in space. The direction of the electric field is the direction of the force that a positive charge will feel. So if I told you, I'm going to put an electron right here, in which direction is it going to move? You should know immediately it's going to move that way. Because the positive charge would feel the direction in the same direction as the electric field. A negative charge will go in the opposite direction. Okay? And of course, the bigger the electric field, the more powerful the force it's going to feel. That's what's great about the electric field. So anyway, I hope this is helpful. If you could do the electric force calculation, the electric field calculation is identical, just without one of the charges. That's all it is. All right, so with that, I will see you next time.